Hello, so in this video we will talk about probability mixtures, and specifically we will talk about special kind of probability mixtures which are known as the parametric mixtures. So if we have, let's start with the definition. So if we have multiple random variables xn, and n can go to any integer with their any positive integer, and with their every variable here has its own PDF. Then if we take a convex combination of all these PDFs, then we will obviously will have another PDF because it's a convex combination, which means that these coefficients, they are all non-negative and they sum to 1. So that's why this will satisfy the condition of a PDF, and the random variable which represents this PDF is known as the probability mixture of all these variables here. Okay. Now a special case of this is that if these random variables are from the same family of distribution, then the probability mixture is known as the parametric mixture. For example, if we have two normal variables with equal variances and different means, then the convex combination of their PDF will yield the PDF of a parametric mixture. Why? Because both of them have the same form of the PDF, only the mean is different. Okay. And parametric mixture, why? Because mean is one of the parameters of the normal distribution. Okay, a special form of a mixture is when this parameter, which is called theta here, and in this example, that this theta was equal to the mean here or mean here. Then if this parameter is also a random variable with some PDF, then we have a PDF, the parametric mixture, the PDF of that one should be, if I call it y, this is equal to this integral. Okay, where this is a PDF and this is also a PDF. Okay, this is also, this is also a form of averaging with respect to the parameter theta. Okay, but we are now learning it as a form of parametric mixture. Okay, now specifically what we will do is we will apply this definition to a Poisson random variable with parameter alpha. So this means this theta is alpha, and alpha is a gamma random variable with parameters this and this. Okay, and then we will show that the PDF in the above equation leads to a negative binomial distribution. Okay, so now we have to start by some tools. So the tools we will use is that this is the definition of a gamma function. This is a definition of a PDF of a negative binomial random variable. Now note that here we are saying it as a sum of continuous functions. Okay, or if we remove this, then we can just say it as f of x is equal to k. This is equal to the same thing, but this guy removed, and then we have to say that k is a non-negative integers. Okay, the other requirement is that q and p, they sum to 1. Okay, similarly we can write Poisson random variable as having a PDF this, and then we can write the gamma random variable as a PDF this. Okay, so then if we start with this one, for here this guy we will put gamma, and for this guy we will put Poisson. Okay, and for theta I will put alpha. Okay, so what do I get? So this is my gamma guy. Okay, and then this is my Poisson guy. So if every term which does not have alpha in it, I can take out. So I have this guy coming out, this guy coming out, and this guy coming out, and then rest is here. Okay, and then what do I have to do? I have to use a substitution. So let's say I say v is equal to alpha over q. So this means that alpha is equal to v q, and this means that d alpha, this is equal to q times dv. Okay. Now if I plug it here, I get 0 to infinity e to the minus v alpha to the not alpha, sorry, not alpha. So I say here vq to the x plus r minus 1 times q dv. Correct? So here I can say 0 to infinity e to the minus v to the x plus r minus 1, and then q r x plus r minus 1, and then q here. So this is q x plus r, and then I will say dv. So this is nothing more than a gamma function because of here. So I have z minus 1 here and e to the minus x here. So this is nothing there. So this is e to the minus v here and v x plus r minus 1 here. So this is gamma of x plus r. And then of course we have q to the x plus r. So now what I will do is, for this guy, I will put this guy. So then my form becomes 1 over r 1 over k factorial. Then I will say p to the r, q to the minus r, and then here I will say gamma of x plus r, and then q to the x plus r, and then I will say x minus k. Correct? Okay. So then what will I say? So this is equal to 1 over, and then I will say this is plus r, and then 1 over k factorial, and then p to the r, and this is q to the minus r, this is q to the x plus r. So to the x, that's it. And then x minus k, and then of course I have the summation k is equal to 0 to infinity. What is this guy? So here we will use the fact that we have gamma to the k plus 1, this is equal to k factorial. Okay. Now this works. Why? Because this x is only, because of this is only available at k. So I can say, so here I will say x plus r minus 1 factorial over r factorial, and then I will say here k factorial, and then k is equal to 0 to infinity p to the r, q to the x minus k. Okay. Now this, since this is a delta function, so this means x is only non-zero at k. Okay, so then I will say, I will remove this summation and I will say k plus r minus 1 factorial, and then r factorial, oh sorry, I should say r minus 1 factorial, and then this is also r minus 1 factorial, k factorial, and then p to the r, q to the k. Okay, so this is nothing more than k plus r minus 1 k p to the r, q to the k. Okay, so this is what? This is negative binomial, and we can confirm it by going here, and we can say that this is exactly what it is. So we have k plus r minus 1 q to the p to the k. So this is these are interchangeable. So this you can say p to the q. So since they both add up to 1, so they both represent the same thing. So p to the k, q to the r here, and here we have p to the r, q to the k. So this is the same thing. So They are just labels, so we can change the label to P and Q differently. Okay. Okay. So then we have proved by just a simple integration and some manipulation that actually a mixture of Poisson and gamma, when Poisson is a random variable with parameter A and that alpha is a random variable with a gamma distribution, this surprisingly gives us a negative binomial distribution. What is the utility of it? One utility that I can think of is that if we want to generate negative binomial random variables, and we can only have the tools to generate a gamma and a Poisson, then I can generate a Poisson random variable whose parameter alpha is a gamma random variable, and I can just integrate it or average it using this, and I can get a negative binomial distribution. Okay, so this is one use that I can think of this approach. Okay, other than that, it's straightforward. I mean, all we have to know is we have to know the definition that this thing exists. A mixture of PDFs gives us a convex combination of PDFs gives us another PDF, and that PDF represents a very random variable which is a probability mixture. And then if the mixing is done based on the parameter of some distribution here, then that mixing gives us a parametric mixture. Okay, and then I mean rest, this is straightforward. I mean once you know that this has some form and this has some form, you can just use integration techniques, several of them, and come up with the final answer. Okay, so this is it about the probability mixture and parametric mixtures. Hope it was easy to understand. Thanks for watching and hope you liked the video.